Hi, my name is Jenna Sailor, and this is my Physics Lab 3 on the black hole. The purpose of this lab was to find the mass of the black hole, to determine the initial velocity of the spaceship in order to get close to and exit the system, and finally to calculate the forces on the planet and on the spaceship. So for the preview, the system is the black hole and the surroundings are the star. The initial conditions are as listed below, and then finally for the results, the mass of the black hole was 1.82 times 10 to the 34th kilograms, and the initial velocity of the spaceship was negative 2.5 times 10 to the 8th, 4.45 times 10 to the 6th, and then 0 in the z direction. So important concepts to understand are Newton's second law, or the momentum principle, and that basically states that the net force is equal to the change in momentum over change in time, or that momentum is equal to mass times velocity. And as you can see below, you can split the second law into two components, the parallel and perpendicular. And the parallel components would be the ones pointing in the direction of movement, while perpendicular is pointing to the center of the kissing circle, which is basically the circular path that an object would move in, even if it's not necessarily moving in a circle. It's also important to know that F net parallel changes the speed of the object, while F net perpendicular changes the direction of the object. And together they equal net force. And then finally, it's also important to know the universal gravitation, which is force of gravity is equal to g times both masses over the radius squared. Now we're going to take a look at the computer model for the first part of the experiment. As you can see here, the mass of the star was changed to whatever was given in the problem, and then for delta t, it was just the 24-hour time period converted to seconds. Down here by lines 164 and 165, we had to edit the lines p equals mass times velocity. And then moving over here, we have just delta v and delta p, which is just v final minus v initial, p final minus p initial. And then right here, dp dt is the same as change in momentum over change in time, which is what we plugged in there. And then the final momentum minus the magnitude of the initial momentum over time. And then down here, just updating the formulas, plugging in the universal gravitational formula, but writing it so it is equal to the mass. And then down here, it's just plugging in the previous equations for the given vectors. After updating and running the code, it printed out the net force and then the net parallel force and net perpendicular force, along with the masses of the black hole as it updated. And from there, averaging all the different masses of the black hole that were printed, giving the final mass, which was 1.82 times 10 to the 34th. What does it mean? Although it asks us to find the difference between the parallel and perpendicular components of momentum and net force, they are actually the same. They're both Newton's second law, and we can restructure the equation in order to get both of them. It's also just important to note that F net parallel gives the speed of the object, while F net perpendicular gives the direction. Now on to the second computer model, which was used to find the initial velocity of the rocket. So here you can see in the code we edited the previous mass of the black hole from the last computer model. Down here on line 61 through 63, it was sort of a trial and error method in order to determine a velocity that would work, so the spaceship wouldn't move faster than the speed of light, but would also not get sucked into the gravitational pull of the black hole or crash onto the planet. And on this side, it was just plugging in the gravitational force formula between the two objects, whether it was the black hole and planet, the ship and the planet, or the ship and the black hole. Then finally down here, it was just position update and velocity update. So as you can see here, the initial velocities that worked were negative 2.5 e to the 8th and then 4.45 e to the 6th. And as you can see in the image down below, the ship successfully escaped the pull of the black hole. What if? So, what if we wanted the spaceship to enter some kind of orbit around the black hole without crashing into the planet and without being sucked into the black hole? Well, in order to do so, the initial velocity would have to be very similar to the one of the planet. However, it would have to be somewhat different so the ship didn't crash into it. And for the velocity, I couldn't actually find the exact one, but it would have to be something around negative 2.5 e to the 8th, which is our starting velocity in the x-coordinate for the initial velocity we found. And then the initial velocity of the planet plus some certain amount that I couldn't exactly figure out. So, errors. I have a very limited knowledge of coding, so obviously if I was better at coding, my results would have been more accurate because my code would have been better. And for the sake of time, I also left delta t shorter than it should have been, causing less precision. If the experiment was to run longer, results would have been more accurate because the summation of all the smaller velocities with the smaller delta t's could have been added and averaged to the final amount. And then for the second experiment, multiple initial velocities were accurate, but I could have continued to guess until I found one that led the perfect trajectory of the spaceship, instead of using trial and error, I also could have used a more mathematical approach. Thank you.